Hey guys, it's Mr. Win. Let's win some chemistry. Welcome to my lesson on heating curves. A heating curve basically tells you the story of ice as it progresses into superheated steam. Let's have your notes out and ready, and let's start from the beginning. In problem 17, we're going to use this heating curve to help calculate the total amount of energy that it takes to bring ice initially at negative 5 degrees Celsius all the way to superheated gas at 135 degrees Celsius. The first thing you have to do is sketch the heating curve. There's two important points that you need to fill in. So the melting point at 0 degrees Celsius and then the boiling point at 100 degrees Celsius. And from there, you're going to draw 5 legs of the reaction. See how it alternates in zigzags? So there's 5 legs, A, B, C, D, and E. You can see where there's a slope where it goes up. I've color coordinated that. So they're in green. You're going to use the equation MC delta T for that. And then where it plateaus, I use blue, so you're going to use a different equation because there's no temperature change. You're going to use M delta H for those. I need to start from the bottom of the graph first. So initially, I'm at negative 5 degrees Celsius, and leg A ends at 0 degrees Celsius. Because there's a temperature change, I need to use the equation QA equals MC delta T. And then I plug in my 3 values. So mass is 35 grams. Specific heat is 2.03 joules over grams degrees Celsius. And then my temperature change is T final minus T initial. So leg A ends at 0 degrees Celsius, and then I'm going to subtract negative 5 because that's where it starts initially. So once I multiply those 3 values together, my total energy for leg A is 355 joules. Leg B represents the phase change from ice to water. So from the beginning of leg B, it's still ice. At the end of leg B, is when you start to see it transition into water. Because there's no temperature change, you see how it goes flat and it plateaus? You're going to use a different equation for this one. So this one's in blue. So this one is Q equals the mass times delta H fusion. Delta H fusion just represents the energy that it takes to change ice to water. So what we do is we're going to plug in 35 grams again, because the sample is still the same for the mass. And then for delta H fusion, you're going to plug in 334 joules per grams. Once you multiply those two numbers, you'll get 11,690 joules. Leg C represents the physical act of heating up the water from 0 degrees Celsius to 100 degrees Celsius. So because there's a temperature change again, we're going to switch back to the equation Q equals MC delta T. Then we plug in our numbers. So for mass, 35. For specific heat, it's now 4.18 joules over grams Celsius. That's a number you've seen before. That represents the specific heat of liquid water, because in leg C it's now a liquid. And then for delta T, T final minus T initial, so 100 minus 0. Multiply those 3 numbers, you'll get 14,630 joules. Leg D represents the transition that water makes into steam. There's no temperature change here, so you have to use the equation Q equals M delta H vaporization. So again, for mass, plug in 35 grams. For delta H vaporization, this is a known published value that is 2,260 joules per grams. You can see there it takes a tremendous amount of energy. It takes 79,100 joules to change 35 grams of water into its gaseous form. To illustrate leg D even better, we could see how it's producing steam. You see in that smaller video image, there's steam coming out of that. So now I take my piece of paper and I put it next to the steam vent, and you can see that it's ineffective at burning the paper because the steam is only at 100 degrees Celsius. You can make superheated steam by placing a Bunsen burner flame beneath the coil. The steam that comes out is now hotter than 100 degrees Celsius, and the steam, the superheated steam, is capable of burning paper. Leg E represents the production of superheated steam. So we're going to revert back to our equation Q equals MC delta T because there was a temperature change. So for M, plug in 35 grams. For C, that represents the specific heat of gaseous water, which is 2.01 joules over grams degrees Celsius. And then your delta T is 135 minus 100. So really that's 35 degrees Celsius that you'll plug in. That represents the temperature change of your steam to your superheated steam. So when you multiply those values, you'll get 2,462 joules. Q total is the sum of legs A through E. So add your 5 values together. I'll get roughly 108,000 237 joules. You may or may not get that exact value. It just depends on how you rounded, but getting a value close to 108,000 is acceptable. Alright, thanks for watching. I hope that made a lot of sense. The heating curve is basically just telling a story. You're going from ice to superheated steam. You just need to understand where the graph starts to have a slope and where it plateaus, and then put those 5 legs of the reaction together, and that's how much energy it takes to bring ice to superheated steam. Alright, thanks for listening, and tune in next time for some more wind chemistry.